Okay, welcome everybody. Today we'll be talking about databases. Before we get started, can everybody hear me all right and see my screen? Great. Any other questions about, let's say, anything related to projects or other things about the class? Well, sounds like we're ready to get started. Okay, so relational databases for today. Relational databases are actually quite important for data science because most of the structured data that we encounter in the real world is probably stored in a relational database. There are other database types. For example, there's NoSQL databases that are object stores and have some performance advantages for certain situations. There is also a new class of databases which are called graph databases, which are really well suited for network data. For example, Neo4j is one of those. There's other databases that are compatible with in-memory object-oriented data structures. These are called object-oriented databases. And so all of those have use, but I think it's quite important to really understand what a relational database is, because I think this is still the most common. You might have encountered this before. And so relational database management systems are still the dominant way to store enterprise data. However, the reason why we're not treating them earlier in this class is because relational databases are usually something that you work with if you're within an organization. So if you were, let's say, working within the University of Utah IT department, you would have access to the student databases, but the actual database is commonly not exposed to an outside party. Twitter has, I'm sure, some kind of database, but they provide a structured interface, the API to it, and so that's the way that most people interact with, outside people, often outside of an organization, interact with the databases. But of course, if you're within an organization and if you ever work for a company, you might have access to their database. So it's not all that relevant probably for any of your projects, but it might be important for a job or a career down the line. And the other thing is that even if you work with a database, usually you have a database server, then you write a Python server, and then you develop an API, even if you're using it internally. So that's also fairly common, because an API kind of makes things simpler, makes them more documented, and also is a security concern, because databases are meant to both read and write, and do things like record transactions and so on. And so they can be very complex, and they can also be insecure if not properly handled. So a lot of security problems that you see in the internet are related to database security problems. So what's the purpose of a relational database? The idea here is that we want to separate data into multiple tables to avoid redundancy. So here's a simple example. If I had say the classical example for a relational database is some kind of store, right, where you have some products, some customers, and some customer information, and then some transaction information. And so if you wanted to store that information, you could do a table like this. So you could say I have a product name, a price, a product description, a customer name, a customer address. And then I could say my MacBook here, my price, then some more description, and then we have the customer name and the address. But storing a data set like this makes it easy for us to work with it, as data scientists, when we want to learn something like the average price of a transaction or something like that. But there's a lot of redundant information. So let's suppose here we have Jack Black 3 times in the rows. And so let's suppose we also have we have the address, and we have a phone number, and we have an email address, and so on. And so if we had all of this information and we would duplicate it every time there is a row for that person, that would be kind of A, waste of space, and B, it will also make updating it. Let's suppose you update your address or your phone number. It would be kind of tedious to update this in every single row. And so what we do instead in relational databases is we break this up into tables of like semantic units. So we would have something like a customers table and the products table, right? So here, the customers table would have the customer name and the customer address. And the products table would have like the product name, the price, and the product description. And so now if you wanted to update a product description, it would like immediately, like you only have to update it in one place, right? You don't have to update it in every single place where you ever use this product description. And how can we now reconstruct all of this is by introducing a third table, which we can call the transactions table. And so here we now capture like we have a transaction, and then we have a product ID, and then we have a customer ID. And so we say our transaction ID, like customer 1 bought product 1, or in transaction 2, customer 1 bought product 3, transaction 3, customer 1 bought product 2. And this is kind of like the way that like relational databases work. We have these keys of every table. So we have a primary key here, which would be the customer ID in this case, or the product ID, or the transaction ID in this case. They uniquely identify the row in the table. And then in another table, we can make references to these other rows. So we can say, like here, we can refer to these. These are called foreign keys, like because they're the primary keys of a foreign table. And so that way we can match up two different, let's say, entries from another table and capture them in a transaction table. And so now if Jack Black wanted to update his address, or if the seller wants to update a product description, they can do this in a single place, and we don't have to worry about like finding all the entries where we ever had Jack Black's address. Okay, so the thing is, like, this is how databases are structured, and what we mostly care about is taking these like relational data tables and then merging them back into a table like this. Like for the purpose of data science, this is really what we want to do, right? If you want to say, if you want to compute how many products did Jack Black buy, or how much money did he spend in total, we want to take those individual tables and then merge them up into one big table, put them into a data frame, and then we can use all of the methods that we had before. And so this is what most of today's lecture is going to be about. How can I like access a relational database, and how can I like merge this into one big table? So we're not going to talk at all about things like updating records in a database and so on. This is something that you don't necessarily need as a data scientist, at least not if you're just doing data analysis. But I'll give you some pointers of where you can learn about this later. Okay, any questions about the fundamentals before we move on to some like technical details? Okay, it sounds like everybody is following along. Great. So now this is the theory, and now in practice, these relational databases are managed in relational database management systems, RDBMS. And they're designed to support read, write, and update transactions. They also support operations, for example, creating tables and so on. And then there's also certain properties that databases have so that they can like remain consistent. So suppose you have like two people buying the same product at the same time, you want to make sure that you don't override anything, right? So you have to make all of these different kinds of guarantees about like consistency in databases, transactional consistency. And so this is like a big part of database research. But we'll largely ignore most of these properties. We're really sticking to reading and querying data, and we'll look at how to get data out of a database. And there's like these two classes. If you're really into databases, there's an undergraduate version of databases, which is about like how do I properly use databases, CS5530. And then there's like a graduate class with like database design 6530, though I think that hasn't been offered in a while because like our database faculty member has left. But those are the two courses where you could learn more about those. And so relational database management systems are typically accessed via a special domain-specific language. That language is called SQL or SQL. People use both of those like pronunciations interchangeably. I'll probably mostly use SQL. So we'll look mainly at queries to read and aggregate data. And so here would be a very simple query. Select star from products. And so this kind of like, you can probably guess, select all of the rows. That's kind of like the star part here from the products table. So that would return the whole products table with all the columns and all of the rows. If you wanted to restrict this in some way, we can use a where clause. So we can say select star from products where the row has an entry in the column price, and that entry is larger than 100. So in practice, we're like selecting all of the products that cost more than $100 from the products table. We'll go through more specific SQL statements and on real examples later. There's also like plenty of tutorials. SQL powers a lot of kind of like the backend of the web. And now we need to talk a little bit about like these specific implementations. SQL is kind of like a standardized language that like many different databases understand. There is like systems like such as PostgreSQL or MySQL or some Oracle commercial databases and so on. And these have like certain advantages and disadvantages. They are really great for like managing like production systems where you have many users and concurrently writing. The downside of all of these three systems here is that they're kind of like tricky to set up. So you like have to run a specific service on like a Linux server or maybe on a Windows server and so on. And so we don't really need that for the purpose of this lecture. So either you will just like speak to an existing server, or you can use what I'm doing in this lecture here. There's this SQLite database. And this SQLite is a single user implementation of such a relational database management system. And so we can use all of these functions, but we have like a file. And that file is like where the data is stored. And that file here is this Chinook.db file. And so this is where like SQLite stores all of our data in the database. And so this is available only for me. And like if I wanted to implement, say, let's a standalone, like a desktop application that uses some kind of like SQL like some relational database structure, SQLite might be like a good use case for that, but it's not meant for multi-user use cases. So, but for us, it is like SQLite is perfect for the purposes of this lecture. And there's also the SQLite Python interface. And SQLite comes also, like it's often used for learning too. And so it comes with a nice sample database. And we'll be using the sample database. And here is the database schema of the sample database. And so these schemas are the way in which we kind of like express what is in a database. And so we have, as you can see here, this is like a shop, an online shop for like digital music and videos. And so we have things like tracks and artists and albums and customers and employees and invoices and invoice items and genres and media types and so on. We can see that like for each of these tables, we have also a description of the columns. And then on the right here, you can see also their data types. So track ID is an integer. Then we have like a n varchar that basically means it's a string. Then album ID, media type ID, and so on. And then this also shows like which of those entries is a key. And we can see here that the track ID for the tracks is a key, or for the artist ID for artists is a key. And then it shows the relationships between, let's say, where we have like a foreign key that we're using in a particular table. So here, the tracks table has a reference to the genre IDs key. So this is like a foreign key that is stored here for the tracks, so that we know which genres is like a particular track of. And similarly, this is like all happening for all of these different relationships. Here's one interesting tidbit. We have like the employee has kind of a self-reference, like the table here, so that we have this reports to field, and so that means that like one employee can be like assigned to report to another employee, and so that would be like the foreign key here is actually pointing to another primary key of the same table. Here's a little bit more of a description, but I'm not going to go through that. I think this is fairly intuitive, and as we'll use it, it will become even more clear. OK, so now we can start querying this kind of database. So what we do is we import pandas, and we import this library, SQLite 3. And let me just clear my output here. And so if we run this, here is kind of like the first piece. We use the we connect to this chinook.db file that I just showed you earlier, and now we have this in the in our connection. And then we can retrieve the cursor on the database, so it's kind of like your pointer. And then we can execute in a SQL statement. So c.execute, select star from albums, and we can then print the first line from the results. And so this looks a lot like what we did when we loaded the file, right? So here we have like retrieved the first one from the album, and we see there's like a key, then there's some title, and then there's another key. So here we've used this cursor for accessing the data. And you can either treat the cursor as an iterator, or you can use the cursor's fetch one method to retrieve a single matching row, or fetch all to get a list of all matching rows. And so we could do something like this. For a row in cursor, print all of the rows. Or we can just retrieve all of the data at once as an array of tuples. Of course, as usual, Pandas has ways of like actually dealing with SQL. And this is what we'll be mainly be using, because this is kind of like the tool that we've been super familiar with. And so this is very similar to our read CSV function. I'm saying pandas.read SQL, and then I'm putting in my SQL statement. And the only thing I have to put in is kind of like the connection that we established up here with SQLite. So this is the parameter that is kind of like specific here. And then Pandas will run will run this query here on this particular database, and then put this into like their like, because it's a read SQL statement, it puts it into like a Pandas data structure. And if we do that, we now get our Pandas data frame that looks like this. And this is, of course, something that we are all super familiar by now. This Pandas, of course, like is only useful for reading data, but we'll only be reading data in this lecture. So it's totally fine to do that if you want to just like extract data. Great. So now, like, it's not always useful to select star from a table. We want to be a little bit more specific. And so now when we want to specify like individual columns instead of the star, we also get only those columns. So for example, instead of select star, meaning everything, I can say only select the title column from the table albums. And so in that case, I would just get my titles here. We have used the kind of like the head function of Pandas, but of course this is in fact much bigger. So if I were like to show you like the first 10 entries, I could do that. But we can also do that, like limit the, like if you just want to explore and don't need all of the data, we can also run like limit the query in SQL. So we can say select title from albums limit 3, and that gives us only the first 3 elements. We can then run more restrictive queries with the where keyword. So we can do something like select star from albums where title equals let there be rock. OK, so like 2 things are notable here. First, like we've been using triple quotes here, and the reason we are using triple quotes is because they allow us to double quotes. They allow us to like break lines like this, and so SQL, it can be like, these can be pretty long queries, right? And so you want to break them up into kind of like semantic lines. And when you use triple quotes, we can do that. And then here we used like single quotes for that particular string. Okay, this is like the equality operator, but we have other operators as we've seen them in other contexts, but they might look a little bit different. So like this operator with smaller and larger than is like the is not operator. Then we have our standard numerical operators. And then we have like an in keyword, which allows you to pass a list of options. We have a between keyword that allows you to define a range. We have a like keyword that can be used for some pattern matching, which is kind of similar to regular expression. And then we can use is null or is not null to test for empty values. And so here are some examples. Well, if let's see, look at first at this example here. We have selected all the columns from albums where the title is Let There Be Rock. And this is, of course, only a single one. And we can see that we have actually retrieved that single row. So now we can use the is not operator like this. So if we want to say everything except for Let There Be Rock, we can do it like this. Select all the columns from albums where title is not Let There Be Rock. And we get all of the albums, and you can see that Let There Be Rock is used to be at position 4 here, or at album ID 4, and it has been removed. Or we can use like a greater than operator. Select all the columns from invoices where the total is larger than 10. So transactions that have like had more than like $10 worth. And then we get like a list of all of these transactions like this. We can use the between keyword, for example, saying like select all the columns from invoices where the total is between 15 and 20. And we would get like the result here, and you can see that this result actually matches our query here. And then we can use the in keyword and pass a list. We can do something like select all the columns from invoices where billing city, like this is this column here, is in the list of Chicago, London, or Berlin. So one of those 3 cities, and you can see that we have here Santiago, Vienna, and then Chicago, Madison, Oslo, and so on. So we have many different ones. And if we run that query, we get like a subset where we only have Chicago, London, and Berlin in our result data set. Then we can do these expressions with like, so that we look for some kind of like pattern similar to regular expression. I'm not going to go too much into detail, but you can do things like select all the columns from invoices where billing city, like C, and then percent. And the percent sign is kind of like similar to like the star sign in regular expressions. And so that essentially means it starts with a C and then continues with anything else. And so now we see that the billing city is all C's, like Cupertino, Copenhagen, Chicago, and so on. We can also query for strings that end with an RT, like analogously, we just put the percent sign before the RT. And so if we do that, we see that Stuttgart and Frankfurt match that particular query. We sometimes we can order, we use the order by function to sort the output. Of course, we can do order like sorting in a data frame, but sometimes it's useful to do it in the database itself. So if I do select all columns from albums order by title, we can see that it starts like it just does lexicographic sorting. It starts with the ... and justice for all, and then with like a numerical value, and then with all of the A's. And then ends with like the W's, Z's, and the square brackets here. Okay, so these were kind of like the basic operations, how I can retrieve elements selectively from a single table. Now, let's do like a quick detour into referencing and renaming it, but then we'll immediately look at joining tables. So usually when we write queries involving multiple tables, I might have, let's say, like a title or a name or something like this might be very common. And so it can get confusing. And so we have 2 options. We can always like use the fully qualified name, like tracks.name, to refer to the name column in the tracks table. But I would also have an artist.name. And so sometimes it's this can get annoying, and I can rename these columns both for representation after the fact and for like making my queries a little bit simpler. So I can rename tracks.name to track name, for example. And if I run this, is like select tracks.name as track name from tracks. And now this would return a table where like the result here, like this doesn't change the database, but my result is now called track name. And that's kind of useful, especially when I start combining multiple columns and I have multiple tables and I have an artist name and the track name and a genre name. And then I can like resolve these ambiguities and make it easier to write these queries, but also make the output more readable. Okay, so we'll be using this renaming all the time, but now let's look at the most important piece of today's lecture. That's joining tables. So like there's generally many different ways to aggregate and group by data with SQL. And we won't be able to cover all of them in detail today, but we will be using like examples with the inner join clause to kind of like resolve a foreign key relationship and roll up these tables. So let's suppose we want to create a table that contains one row for each track, but that row should also contain the album title. And so if we look at the tracks table, we can see that we have like a name, we have a composer, we have some other like metadata about this, and then we have these foreign keys to album ID, media type ID, and genre ID. And like now we want to replace this album ID here with the album name. We can similarly look at the albums table. Here we have our album name, our album title, and then our album ID. So this number here is a foreign key and points to the primary key in this table here. Oh, this is actually the primary key. This is just the raw information from pandas. So like this would be, if we looked at the schema, this is a relationship that we care about. Tracks has this foreign key album ID, which is the primary key in the albums table. And we want to kind of resolve this relationship so that we get, like, instead of having a 1 here, we want to see for those about to rock, we salute you. So that's the goal here. And we can do this with the inner join statement. And so here, like, is this multi-line statement. I'm selecting the track ID, tracks.name, and then I'm renaming it as track, albums.title as album from the table tracks, and then I'm doing an inner join albums on albums.album ID equals tracks.album ID. Okay, so if I now execute this, I get exactly what I wanted earlier. I get the track name and then the album name next to it. Okay, so let's take this statement apart. Here we chose what to select, and we also rename the columns with the as statement. So we can see here, like, this is not name now, but it's just the track, right? And this is not the title, but this is album. And then this is kind of where the magic happens. We say that the tracks and the albums table should be joined based on this relationship here. So here, like, the tracks should be inner joined on albums based on this relationship here. And that's where this is where we, like, combined with the albums.title, this is where we kind of like make this resolution and retrieve the relationship between, like, the foreign key in one table and the primary key in the other table, and then retrieve that value and then map it up in this one result table here. So based on this inner join, you can construct flat tables out of databases that you can then use in the data science process. And with SQL, you can also do various other things, such as like group by or aggregates. And we'll talk a little bit about these, but we can do many of these group bys and aggregates and computing averages and so on with pandas, so that the joining piece here is really the most important one. That's the thing that we can really, like, barely do in another way. So if I have a relational database, and I know how to work this inner join or these joins in general. I'll talk more about other joins. And then I can extract this in a pandas table, and then I can do everything that I usually do in a data science process. So that is kind of like the most important part, that you understand how these joins work. And so now I'll do a couple of more examples here, and then I'll talk about other joins. So now, like in this table, we now have tracks and albums, but we still don't have the artist name. So we want to also have the artist name in here. And so we can do that by saying select tracks.name as track, albums.title as album, artists.name as artist from tracks, and then I'm doing my inner join albums on albums.albumid is tracks.albumid like before. But then I'm doing a second inner join, artists on artist.artistid is albums.artistid. And again, based on like how I specified those here, this will now show up with like the track name, the album name, and the artist name, exactly the way we wanted it. Okay, and then finally we can combine this with like a where condition to get a more specific result. So for example, if we wanted to look at all of the Rolling Stones tracks in this data set and print them like this, we could just add another line here where artist.name is the Rolling Stones. And that here gives us this desired result. Great. So I mentioned like there's different types of joins. So what we've done so far is we have joined tables up where we have a perfect relationship between a foreign key and a primary key. But that's not necessarily always the case. So let's suppose we have a table like this. We have an artist table where we have a primary key, artist ID, and then we have a tracks table where we have tracks ID, a foreign key, artist ID, and then a track name. But notice that I have like Neil Diamond here with artist ID 2, and he's not referenced out of our tracks table. So there is like Neil Diamond is in this table, but he doesn't have a song in the tracks table. And so if we did an inner join on those two tables, what we would get out of it is we would just get the ones that perfectly match. So we could get the like two Tenacious D songs that we have here. That would be the results. But we would not get any information about Neil Diamond. We wouldn't even know that Neil Diamond is in this table from this. And so this is often what we want, but not always. Sometimes we want to be explicit if there is like some missing data. So here, this like for this table here, we would want to get like if we want to have these tracks, we could have like a track name none and Neil Diamond and an artist ID 2. So that could be like a table that makes sense in some contexts, right? Like maybe not so much here if I really want mostly a tracks table, but you can definitely imagine other situations where you want to match up information if it's available. But if it's not available, you still want to keep it. Let's suppose we have, like, say, a tracks, like a chart information about a track. Some tracks never enter the charts, right? So there might not be an entry about that. But for those where we have chart information, we might want to add this to this table. So instead of doing an inner join, we would here have to use a left join, which gives us all of the values of the left table, so the kind of the first table, no matter if there are matches for the right table. And so the way to do this is, like here, we select artist.name as artist, albums.title as album from artists, and then we run a left join albums on albums.artistid, artist.artistid. And then I'm ordering here by album ID, because then we can see that there are some some tracks by artists, or some artists that don't have a reference to the album table. So you can see that there are some artists that don't have an album in this particular database. And if we ran an inner join here, those wouldn't show up. And so, like, obviously, if there's a left join, you would also expect that there's a right join. And yes, there's two other types of joins. There are right joins and outer joins. Both of them are actually not directly supported by MySQL, but by SQLite, sorry. But they can be, like, this is actually wrong. This should be SQLite. But you can emulate them. So like right join is easy, right? You just exchange the order. And like an outer join is like basically looking both ways. So if you're missing values in either table, the entry would still be in there. And there's this article here that describes this nicely with Venn diagrams. And so you can see like the inner join is if you have values for both of them. The left join is if you have values for both of them or for the left one. The right join is if you have values for both of them or the right one. And the outer join just like matches everything up independent of missing values in either of them. And then you can go further and like have excluding joins and so on. But yeah, so those are not directly supported in SQLite, but that's okay. Like probably like with inner join and left join, you will get like 99.9% of the use cases. Great. So before we go into grouping, let's just take our 5-minute break and we'll resume at 1:08. Okay, so just because I think this is really the most important piece, I'm just going to recap quickly the whole joining piece, right? So the idea is that we want to match up different tables and integrate the data between those different tables based on this like foreign key, primary key relationships. And we do that here in this example by essentially like we select the track ID, tracks.name as track, and then here the albums.title as albums. Like here we refer to the table that we're later actually like only touching from the join. So then we say like, where does this come from? From tracks. This is our primary table. And then in the inner join, we refer to our secondary table here, the albums, which I'm referring to here. And then with the on, I am specifying what is the, like, how do I want to match them up based on albums.album ID equals tracks.album ID. And so here, this is the primary key of the albums table. And then here, this is the foreign key pointing to the primary key, the foreign key of the tracks table pointing to the primary key of the albums table. And that's how we get this thing resolved. And we can do that with like joining multiple tables. So we can kind of reconstruct all of the information of a track based on kind of like sequencing multiple inner joins and kind of like integrating all of the instances where we have a foreign key in the tracks table and then resolving the actual data that we care about for that particular record. Okay, so and then yeah, to recap, left join returns values that match between both tables. If we do like a inner join returns only values that return both tables. Left join returns all the values in the left table, even if the right table that we're joining on doesn't have an entry. So if we had, let's say, like a missing entry for an artist, the track would still be listed in a tracks table if we had used a left join instead of an inner join there. OK, any questions about this before we move on? Great. So now the other thing that you can do with SQL is doing things like group by. And we've seen group by before for data frames. And of course, we could just use pandas group by since we'll be using data frames anywhere. But sometimes it's useful to understand how, like, to use SQL-based group by. It can be much more efficient just to get the right data out in the first place. And some database research in the last, let's say, decade really looked at how can we do kind of like approximate and intermediate analysis based on these kind of aggregates with very large databases. So like Fei-Fei Li is like a former faculty member at the School of Computing, and he developed extensions to the PostgreSQL database where you could run things like counting or averaging and so on like databases with billions of records. And the database would give you very quickly a good estimate and would keep refining the estimate as time progressed. And so you would have this kind of like intermediate feedback, even if you have like terabytes of data stored somewhere. And Fei-Fei is now actually like running the database division of Alibaba. And so he's applying this kind of research on a large scale in a commercial context. So, and that's why group by is like all of the stuff we'll be doing on this sample database here. Of course, I could just do this with pandas. But if I have a really large database, the databases are optimized to do these operations, right? And so you don't have, and they also don't do it in memory. And so you can work with much, much larger data than you could do with pandas. And so this is where you like might want to use a group by with SQL instead of using it with pandas. OK, so it's very familiar. So we have like we group by something, and then we do something with these groups. And as in pandas, we can just use, for example, count as like a simple a simple function that does something with the groups. And so let's suppose we want to use we like a statement that gives us the number of tracks on an album. And we can use the count aggregation function to do this. So here we select album ID and then count. This is like the function call of track ID as number of tracks. So here, this is kind of like the interesting piece from tracks, and then we say group by album ID. And if we run that, we get this here. We get like our album ID and how many tracks does it have. And we see that the album with ID number 2 has only 1 track, but album with ID number 3 has 3 tracks. Of course, these albums IDs are unreadable, so we want to combine them with album titles. And so we can first do the inner join here and then do the group by. So we can do select albums.title as albums, count tracks.track ID as number of tracks, from tracks, do an inner join, albums on albums.album ID equals tracks.albums ID, and then finally do a group by tracks.album ID. And now we get kind of like this human readable thing where we have the album name and the number of tracks. And so here, just to like recap, we have to do this inner join because the album information of the title isn't in the tracks table, right? Like we're doing this from the tracks table. And if we looked at the intermediate here, we would just like have a table like we had it up here, like this, where we have all of those explicitly. But then in the next step, we are looking at all of the Voodoo Launch albums tracks, for example, and then like group them, put them into one group, and then apply the count function to it, and then we get the count for the number of tracks out of this function here. OK, and then we can combine this with filters. We can use the having keyword, which works a lot like the where keyword, but instead of like just filtering something, it applies to aggregate functions. So here we use the having count function. So now we run select albums.title as album, count of tracks.track ID as number of tracks, from tracks. Then we do our inner join. Then we group by tracks.album ID. And then we include this condition here, having count tracks.track ID is larger than 15. And that now results in a list of albums with their names only if the tracks here are larger than, the number of tracks is larger than 15, which we can see is the case for all of those here. And of course, this is kind of like this is like here we are doing this count twice. So we're doing it here once, and we're doing it here again. And so instead of doing that, we can also just use this expression or this variable name that we have redefined here directly. So that's actually a little bit easier to read. So this is exactly the same thing. The only difference is here that I'm like not using the count again, but I'm just reusing the variable that I've already defined, and that will result in the same table. There are several other aggregate functions. For example, I can use average, max, and sum, and then we can also do some simple math. For example, here we'll convert milliseconds into minutes, and so like this would be an example of like let's look at the result table that we get here. We get the albums, how many tracks does it have, what's the average track length, what is the maximum length, and how long does the album run in total. So that would be like this information, like all of these 4 columns are not contained in our data set explicitly, right? I'm creating them based on information that is available in the tracks, and I'm doing then these various operations on them. And this is now like essentially preparing for doing some data analysis subsequently. And so now let's look at this in detail. What's going on here? I'm selecting the album IDs from the tracks table, the titles, I'm renaming it as albums. Then I'm counting the tracks and this is kind of like the result that we have here. We could kind of like do this, rename this as number. That might be a little bit more elegant. And then here are some of these new things. So we take the average of the tracks at milliseconds based on the group by we have, and then we just divide this into minutes. Like we make this into minutes, and then we have the max, and then we have the sum, and we also convert this into minutes. And then the rest of this is familiar. We're like the tracks is our primary table. We join albums, and then we group by tracks.album ID. And then I'm also ordering so that we have the longest average track length here at the top. And I'm saying this should be descending. And then I can see that, oh, I actually have some TV shows in my database here, like Battlestar Galactica Season 1 has 24 episodes. Average length is 48 minutes. The max is 49 minutes. And then in sum, it runs for like 1,170 minutes. And now I have that for all of those different aspects. And so that would be how I could use SQL statements to prepare a data set that I could then do anything else that we learned about in this class too. OK, any questions about this before I move on to the last section of the class? Great. So one thing I wanted to mention briefly, and it's not super relevant to data science, but I think it's useful to just like know about it, is security. As you know, like, and I mentioned this earlier, like because these databases can be written to, it is pretty like dangerous to give people access to those databases. And one thing that is very common is like, if you create a new user account for any website, what's happening behind the scenes is that the field, like the web server takes some information from you, your address or your name, and writes that into a database by running an SQL statement. Now, if you were a malicious user and the database was done naively, you could, in theory, write a username that actually damages what's happening in the database. So like in practice, like we've always done like these SQL statements here where we have specified everything exactly, right? We've said exactly we want these kinds of things. But what you could do is I could do something like use a Python variable, right? And that Python variable could be user specified. So somebody could put that in, and I could just run a query like this. Execute script, select everything from albums where title is this, use your illusion in this case. But the point here is that the title here could be variable and could be user specified. And so I'm actually running a piece of SQL code here that I don't have fully under control. Somebody could write something in this title variable here that could be malicious. And so if we look at like all of the different tables that we have here, like here I'm just SQLite master is a special table that contains a list of all the tables. And so here we have a list of all the tables in our SQLite database. We can see that we have albums, artists, invoice items, invoices, and so on. So now if we were to read title from a user, and like this user would be malicious and try to kind of like destroy our database, they could write a and then like quote, semicolon, and then drop table invoice items. And so that would be a problem, right? Because if I just like executed this, the semicolon here tells SQL that, well, this is the end of a statement. Now another statement starts. And the other statement in this case is delete this table. And obviously, this isn't what I want, right? Like I'm expecting here a string, a harmless name. But if I'm running this like that, I will actually execute that statement. And so I can actually show you. if I have this, like here's my title, this is, if I execute it just like I did before, like we can see first, this is the statement that is executed here. Select star from albums where title is A, semicolon drop table invoice items. This throws an error, but it actually doesn't matter, because if we look, we can now see that the invoice items table that we have deleted here is now in fact gone from our table. So this was an example of successful SQL injection. This is kind of this is what this hack is called, right? If you like don't sanitize your SQL statements before you execute them on a database, that can be very, very problematic. So you have to be really careful about like if you ever work on a database, you cannot just take a user input and like assume that it is a safe part of any SQL query. And so there's a couple of ways that you can avoid this. First, like now it's actually gone from the table. So if you wanted to restore this, you have to go back and like replace this chinook.db with the backup version of this database. So you have to copy that over and rename it. Otherwise, there's no way to get this back now. So that's why there's those two files here. So there's no way to recover this, and this is of course like a big problem. And so to avoid problems like this, there's lots more to security, but I'll just give you a hint here. You should use, let's say, like here this question mark for substitution and pass in a tuple. So we've seen this in for Python before, and similarly, this works for like with this library that we are using here. I can say select star from albums where title is question mark, and then pass in this title tuple. And that will actually not, this will execute only the single statement, and it will not execute this piece here. This will make sure that no additional statement will be executed. So if I, like here, I'm actually dropping table playlist, or I'm trying to, and if I run this statement here, as you can see that I did that here, my playlist table is still alive and well. So this was kind of like successfully prevented that particular attack. And so if you wanted to use this same example with safe code, this would be it. And so like this has been something that has been, of course, made fun of a lot. And so like there's this XKCD comic. Definitely read that if you care about XKCD at all. And so that wraps up databases. And there is an exercise where that you can use for one of your activities. This is just like doing a couple of simple queries, and then some exercise, some example for joining. And so if you still have an activity to do, you can submit that as your activity. If not, I still recommend you do it, because of course playing with it is a little bit more like educational than just hearing me talk about it. But I'm happy to take questions, and otherwise I'll start opening breakout rooms in like 2 minutes.